Hi Satyam, hi Fida, can you hear me? Hmm, am I audible? You can type in the chat. Okay, cool. Okay, so let's start. Uh, so today we'll cover week four's content. So what was covered in the lectures were MM type queues. So I'm just kind of removing one of the other parts. So as we know that, so in a queue you will have in any queue, you will have arrivals, let's set to rate lambda per second, and you'll have departures at a rate mu per second. So in MM type queues, both the arrival and the departure process. So this is the arrival process and this is the departure process. Both will be of type Poisson, right? So the number of arrivals uh, in a particular time interval. So, and the number of departure in a particular time interval will both be distributed as a Poisson process with a mean rate, lambda and mu respectively. So let's say number of arrivals as a function of time. And like I should write it as the probability that number of arrivals as a function of time is equal to n is equal to something like e to the power minus lambda t whole to the power n by n factorial, n greater or equal to 0. And similarly, Poisson, and similarly, another mass function will be number of packets or number of elements in the queue that have completed this service. This is also distributed as Poisson, right? So this is the general framework that we have, M type queues. And so depending on the number of servers, you can have MMC, which means that there are C servers. And then you can have another variation, which is something like MMK, some other value M. Now this is a scalar M. This is not denoting exponential. So what this means is that this is the Q, or if you use it in a networking constant, a buffer limit or capacity, let's say. What does this mean? That all this means is that the queue will reject, has a capacity of m. So once there are m elements in the queue, any other packet or any other person or whatever you're modeling as a queue, anything else that comes in is actually rejected. You won't allow any further entry. So we will mostly deal today with various problems of that involve these kind of queues, and how do we solve them, right? So for today's lecture and for many subsequent lectures, I will refer to a classic queuing theory textbook, and I'll be solving problems from that textbook essentially. So I will share. I mean, I have already shared actually the drive link, the name of the textbook. So, and I've provided the link and the download links as well. It's a textbook that is freely available. So 1 second, I can just share my screen from here and show once. I will probably upload the PDF as well. So you can check in the drive link that has been shared with you. You should find this document called Bertseker's Gallagher book link. So this is Data Network, second edition. It's a freely available textbook by Professor Bertseker and Gallagher from MIT. And so what I'm referring to is chapter 3 of this textbook and the problems in chapter 3 of this textbook. So I'll be referring to the problem numbers as I go forward. And the solution manual is also freely available, prepared by various authors. And so you can refer to the solutions there for a discussion. But I've picked a few problems from this textbook. So this chapter essentially covers bulk of the topics that are about to come in this week and the subsequent weeks. And so every week I'll try to pick some problems from this textbook and solve it for you, and that should help you with your assignments. You'll get, you can expect similar kind of problems that will be asked. Okay, so I'll start. I'll just switch back to my tablet. Okay, should see my tablet again. Let's start with the first problem. Unless there is any other doubt you want me to clarify first, I decided to go ahead with problem solving because the theory in this part is relatively straightforward. It's more about how to understand problems. But if there is any doubt, I would like to address it first before. Am I audible? Satyam dropped out. Okay, yeah. Thanks for that. So I'll start. So, okay, so the first problem is, so this is problem number 3.13, part A of the book. You can check it out, but I'll kind of draw the problem for you. Very simple. So you have a taxi stand, right? So I'm just writing it here, a taxi stand. And so at any time, so there is a room for like, so in a taxi stand, there is room for W number of taxis. So at any time, you can accommodate at most, you can park at most W taxis. And you have people arriving. So this is like, you have people arriving at the taxi stand to board a taxi. As a, the classic assumption, Poisson process, arrival rate is lambda per second. Okay. And then you also have taxis. So this is taxis also arrive at the stand, right, in a taxi stand. And so taxis are also arriving as a Poisson process with a rate mu per second. And so what happens is, so for people, the behavior is pretty simple, right? They arrive, they book, they board any one of the taxis. Let's assume they have no preference, and then they leave. For taxis, if I have to draw a car here, something like this. For taxis, what happens is, if the queue is, if the taxi stand is full, if all of the taxis and all of the parking slots are full, then the taxis will leave, right? Otherwise, if there is a customer, so let's say there are people waiting here for taxis and a taxi comes into the stand, it will pick up the customer, right? The customer will get the taxi. And if there is no customer waiting, then it will simply join, and there is space available, it will simply join. So you have taxis here. This is the setup. And so what you really want to, one second. So you want to try to kind of get an idea of how many. So in the first part, like you want to find out the distribution of the taxi queue size. Taxi queue size n. N. So this is essentially the number of taxis that are at the stand, that are waiting at the stand for a customer. You want to find the probability P of n, where n obviously can be 0 less or equal to. So n is obviously equal to 0 to 1 to a maximum of W, right? You can have at most W taxis in the stand. You want to figure out this probability, and how do you use MM1 queuing theory for that? So this is slightly non-trivial. It's not an easy problem to think straight away, but it's. I thought I should discuss this kind of a problem. So the hint here is that you have to use MM1Q in some sense, but how? Right. So now let us denote n. Let us denote n to be, actually, okay, let me make this size as q. Denote this as q. Right? Let us denote n to be number of people waiting plus number of empty taxis, right? Or empty taxi slots, let's say. Okay. So now what happens with this is, so let's how does this quantity behave? So it goes from n to n plus 1 when one person arrives, right? So this is arrives. So this is at rate lambda per second. This is a Poisson process. Then it goes to n minus 1 when one taxi arrives, right? Because this is number of people waiting plus number of empty taxi slots. So when a taxi arrives, it either picks up one of the people who are waiting, so then it reduces it by 1. Otherwise, if there is nobody waiting, it just fills up one of the empty taxi slots, right? So then the number of empty taxi slots goes down by 1. So one taxi arrives at rate mu per second. Okay. So then this behavior is like an MM1Q, right? You have a Poisson arrivals, which push the state from n to n plus 1, and Poisson departures, which push the state from n to n minus 1, right? So we know that the distribution here of the probability that the state is n is something like 1 minus rho by rho to the power n, where rho is nothing but lambda by mu, the ratio of arrival rate to service rate. This is kind of check in the theory. This is the derivation here. Okay. So okay, so now maybe so now the question is, you are provided some values. You are told that lambda, the arrival rate, is, let's say, 1 per minute, and mu, the arrival rate of taxis, this is arrival rate of people, arrival rate of taxis is 2 per minute. So which means this is an MM1 queue as discussed, where it behaves like an MM1 queue with an arrival rate of 1 per minute and departure rate is 2 per minute. So then, and you are also provided that the value W is equal to 5. That is, you have 5 taxis can wait, essentially. Can wait. Okay. So, fine. Now, let us check which are the values n can take. Now, clearly, the lowest value n can take is 0. Okay. N equal to 0 because there's nobody waiting and all taxi slots are full. And the highest value it can take is 0, 1, 2. The highest value it can take is W, or in this case, 5. W equal to 5. Because you can have theoretically a situation where there is like, yeah, so there is nobody waiting, but let's say, and there are no taxis either. So then you have empty taxi slots equal to W, and so then this you cannot exceed W, because let's say you are in this situation where empty taxi slots is equal to W, then whenever somebody comes in, they will take a cab and leave. So yeah, but that's kind of the idea. Actually, this can move to W minus 1. Actually, like, sorry, this can go up to W minus 1 when taxis are waiting. And when W onwards, this is when no taxi waiting, no taxi situation. So you can have a situation when there are no taxis, but people are coming in and coming in and coming in. So then you can theoretically go to infinity. So yeah, so that is the no taxi situation. But if there are taxis, you cannot exceed W minus 1. Anyway, so let us, so you want to kind of get the probability of number of taxis waiting, right? So you want to find probability that Q taxis are waiting. Now, if you think, so okay, so when n is equal to 0, that is, you typically, this essentially means that number of people waiting is 0 and number of empty taxi slots is also 0, right? Because both of these quantities have to be positive. So that means you have no empty taxi slots. That means you have 5 taxis waiting. Like, we are taking W equal to 5, so you have 5 taxis waiting, right? So n equal to 0 corresponds to 5 taxis waiting. So then what will be the probability of it? We just put n equal to 0 over here. So which means, so probability is P0 equal to 1 minus rho, which is lambda by mu. Lambda is 1 and mu is 2. So it's 1 minus half. So that's half, right? So this is the probability that 5 taxis are waiting. Now what happens when n is equal to 1? When n is equal to 1, it means that like 4 taxis are waiting, right? Because Because if n is equal to 1, that means there is either, so there is one person waiting and there are no empty taxi slots. So that can be, that cannot be the case, right? Because then the person would have immediately left. Why is the person waiting? So when n is equal to 1, then you have essentially one empty taxi slot and there is nobody waiting. That's the kind of the only feasible situation. So then one empty taxi slot implies that there are 4 taxis that are waiting and one slot is empty. So you have similarly 4 taxis waiting. And so this, by putting the value of n here, you can solve it as P1 equal to, again, 1 minus rho, which is half, divided by rho to the power n, which is, again, let's actually just quickly end this. Rho equal to lambda by mu equal to half. So this gives us a number. So 1 minus rho, which is rho, divided by rho to the power n. So half to the power n. To the 1. Something wrong. So anyway, the logic flows. So when n is equal to 2, you have 3 taxis waiting. When n is equal to 3, you have 2 taxis waiting because 3 slots are empty. When n is equal to 4, you have 1 taxi waiting. And then P no taxi is waiting is given by 1 minus summation Pn from n equal to 0 to 4, right? That's the only way. So sum of all probabilities is 1. So if you just subtract everything, then you get this one. Then just quickly calculate these values and see. Right. There is something wrong. I think this shouldn't be, yeah, this, sorry, I think I wrote the formula wrong. This should be rho to the power n times 1 minus rho. And so this will be 1 minus half, this will be 1 minus half times half. So this is 1/4. This will be 1 minus half times half squared. So this is 1 by 8. Similarly, this will be 1 minus half times half cube, 1 by 16. And similarly, P4 will be 1 minus half times half to the power 4. That's 1 by 32. And so probability of 5 taxis waiting is half, 4 is, yeah, so 4 is 1 by 4, and 0 is, I have to just sum all of these up. You can calculate this very quickly. So this will be nothing but 32. If you take LCM, you'll have 16 plus 8, 24 plus 4, 28 plus 2, 30 plus 1, 31. So 1 minus 31 by 32 is nothing but 1 by 32. So then you can write PQ equal to, for various, PQ equal to like 1 by 32 for Q equal to 0. And yeah, I can just fill in the values. 1 by 16, q equal to 1, 1 by 8, q equal to 2. And you can just kind of fill in the values, or maybe even come up with a general expression. Actually, this is also 1 by 32. 1 by 16, 1 by 8, q equal to 1. Mm, Hello, sorry for the glitch. Okay, so I'm back. So we are done with this problem. Let's move on to another new problem. So this is again from Robert Cephas and Gallagher textbook. I'm picking problem 3.15. So here, this is more mathematical. So you have an MM1Q, but there is a change. So like you have a standard MM1Q, but let's say from many transitions, you reach a state when Q becomes empty. So let's say, so after the queue becomes empty, so initially you have packets or people arriving in the queue and then people leave, and at some point you have your queue is empty. So after queue is empty, you have some rule that service resumes after K customers are present. So this thing, let's say you're in a shopping mall, in the cashier counter, you have some queue, and people are moving in, and there is a cashier seated here on a chair, and so there is some desk, and so people are moving in and moving out, and so at some point the queue becomes empty. So then you will wait until K customers are in the queue, and only then you will open the counter, right? So that you have some kind of restriction here. It's otherwise it's an MM1Q, exponential arrival, exponential service. We can assume service rate mu, arrival rate is lambda. But there is this constraint that once queue is empty, you will wait till K customers are present, and only then you will proceed with the service. So now you want to find out the three quantities. One is probability that there are n customers in queue. Two is average queue length, expected number in the queue, which is, we know how to calculate it. It is nothing but summation n times Pn n equal to 0 to infinity, right? This is how we compute average. We know the probability, so we can take a weighted average. And then the third quantity is expected delay or expected delay. So this we know, this is by Little's law. It's nothing but 1 by lambda times expected number of people in the queue. This comes from what we know as Little's law. Little's law. So essentially, once we solve for this, the other parts get solved. We have to solve for Pn. And so the critical question here is, how do you actually even like sketch this system, draw this system? So that is where it gets a little tricky. So here is how the transition diagram will look like. Let's try to draw it. Before any maths, let's try to draw it. So we are at 0. And so when the queue is empty, so let me draw it intentionally in this way. So when the queue is empty, we will go to a state 1 prime, and then, so we let the queue build up initially, right? When the queue is empty, and so on and so forth. And we let the queue build up till the point K minus 1. And I'm denoting it as prime intentionally. So the queue builds up from 0 to K minus 1. Arrivals keep coming in. And then once the kth packet comes in, only at this point will I begin service, right? So obviously, if there are future arrivals, let's say K plus 1, and so on and so forth, it keeps on happening. So this is lambda, and this is mu. We have only one server, so it's an MM1Q. So all of the future transitions look like this. So arrival at rate lambda, departure at mu. And so does, so once there are k customers in the queue, like again, departure will bring us to k minus 1 and so on and so forth. So you have 1, 2, and so like lambda mu dot 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 lambda. So all of these behave the same. So, right, mu, and then if there is a departure, it goes straight to 0. So this is the key difference really. So in a normal MM1 queue, what you will have is 0, 1, 2 states. You will have a lambda transition here and a mu transition here. This has been broken. So this one state you can think of, it has been broken down into 2 parts. It has been broken down into 2 parts, and then the 2 parts are 1 and 1 prime. So when you are in the 1 state, if you have a service, you'll go to the 0 state, but you cannot begin service from 0. If you go to the 1 state, you cannot begin service. So you have to keep building your queue till k, and only then you can start service. So this kind of leads to this splitting behavior, because from 0, if you have the transition lambda, you cannot transition it to 1, because then the diagram will say that, okay, there'll be a mu transition from 1 to 0, which will not happen immediately. You will not begin service when you are building up from an empty queue. So that's why you have to take this separate route and begin service when queue length is k. Okay, is this kind of clear? The rest of it is just algebra. Okay. So one if we check this kind of parallel line of transition, then we can write from here that from the global balance equations, we can solve at each of these states, right? So lambda times P0, rate of inflow in the state 1 prime, has to be same as lambda times P1 prime, right? Inflow is equal to outflow. So this will give me P0 is equal to P1 prime. And similarly, if we solve for all of these till k minus 1, we'll see that inflow equal to outflow. So this will give me, this is equal to P2 prime, this is equal to K minus 1 prime. So because all of these will have a similar equation. So lambda times probability of the previous state is equal to lambda times probability of the following state. So we have this equation firstly by solving this part of the chain, by solving the lower part of the chain, right? This will give us this. Now, another, so this is what we call as global balance equations. Now what we can do is, we can try solving global balance equations for these groups. So let's start with 0. So for 0, arrival rate of inflow is mu times P0, and rate of, mu times P1, and rate of, because it's coming from 1, and rate of outflow is lambda times P0, right? So P1 equal to lambda by mu times P0. This we can solve for. Now, if you see this system 1 and 1 prime together, there are 2 ways you are having an inflow. You are having an inflow from 2, and you are having an inflow from 0. So you can solve it as something like mu times P2 plus lambda times P0. And the outflow will be lambda times equal to, and the outflow will be firstly mu times P1. So this is an outward transition. Mu times P1 plus lambda times P1 plus P1 prime, right? Because you have two outward transitions over here, which is arrivals at 1 and 1 prime, and one inward transition from, and one outward transition on the left side, which is towards 0. So if you solve this, actually, if you put the value of P1 here, so then you will see that lambda P0 will cancel out because P1 is lambda by mu times P0. So what you will have is mu P2 equal to lambda P1 plus P1 prime, something like that, right? And we also have P1 prime equal to P0 from this equation. So you can put it here, and then so this becomes P1 prime. So this becomes lambda times P1 plus P0. Okay. So this is, yeah, this is kind of one result. And similarly, if you solve, actually another way of solving global balance equations is, if certain properties hold, you will typically have a local balance too. So you can kind of draw vertical lines of similar transitions and then try to solve for local balance equations. So from local balance equations, but I don't encourage this technique usually because it's risky. Sometimes you won't have the required properties. But from local balance equations, so you can see that if you make this cut, then you have two transitions, mu times P1 and lambda times P0. These should be equal. So mu P1 equal to lambda P0. And then from here, if you make this cut in the Markov chain, you will have lambda P1 plus lambda P1 prime is equal to mu P2. So you will have mu P2 equal to lambda P1 plus P1 prime. So you get the same equations as you got earlier. This will also be lambda times P1 plus P0. So anyway, in general, if you also try for the other states, you will have mu times Pk equal to lambda times mu P2 equal to lambda P1 plus mu times Pk will be equal to, because if you take a cut here, cut here, mu times Pk will be equal to lambda times Pk minus 1 plus P of k minus 1 prime, which is lambda times Pk minus 1 plus P0. Where, so Pk minus 1 prime is equal to P0. So you have this set of equations. And so this is for all of the states that are in this messy zone. After this, after there are k elements, the transitions are much simpler. So for all, so mu P, if you just take a cut going forward, so all of these states, you will see inflow equal to outflow will give you both directions if you have to balance. So you have lambda times Pk equal to mu times P k plus 1. So in general, you will have mu P I plus 1 equal to lambda times Pi for all I greater or equal to k, right? For all I greater or equal to k. Because going forward, it's a simple MM1Q. It's up to the point k when there are changes. Going forward, it's a simple MM1Q. So you'll have the same kind of transitions. And on top of this, we have this, of course, the general identity that So sum of all probabilities is equal to 1. So P0, certainly P0 plus summation over all Pi prime from I equal to 1 to K minus 1 plus summation over all Pi from I equal to 1 to infinity. So sum over all the states has to be equal to 1, right? Again, let's look at the diagram. So P0 plus sum over all of these 1 prime, 2 prime till K minus 1 prime states plus sum over all the other normal states from 1 to infinity. Everything has to add up to 1. So if you solve all of these equations and if you use the commonly used notation, which is rho equal to lambda by mu, this is commonly used in queuing theory because the expressions are always in terms of lambda by mu. So we might as well use a common notation. So yeah, so again, if we actually check this, so from this equation number 1, we can see that P0 equal to P1 prime equal to P2 prime equal to Pk minus 1 prime. So straight away this summation, since all of the values are equal and equal to P0, we can write it as K times P0 plus summation I equal to 1 to infinity Pi equal to 1, right? Because all of the Pi primes are equal to P0. Okay. And so now what we can here check is for, okay, so now P1 is clearly rho times P0 because P1, if you take lambda, P1 is lambda by mu times P0 and P2 is rho times P1 plus P0, right? And then P3 is rho times P2 plus P0, which is rho times P1 plus P0 plus P0. So that is rho squared times P1 plus rho times P0 plus P0, right? So similarly, you will have and then let's substitute for P1. P1 is rho times P0 in itself. So you'll have, actually no, this is rho squared times P0 plus rho times P0. If you multiply rho towards the inside. And then P1 is rho times P0. So you will have this as rho cube plus rho square plus rho times P0, right? And so in general, you will have Pi. So if you extend this, you will have Pi equal to, you take rho times common and P0 common, and then you will have 1 plus rho plus something like rho to the power I minus 1. That's what you'll have. So which is, yeah, so which is nothing but P0 times rho 1 minus rho to the power I. So this is my GP series formula by 1 minus rho, because we know rho is less than 1. So or more specifically, 0 less than rho less than 1. So this is by the formula of the GP series. And so this is the formula for Pi. And so this is, but this is for all i's less than k. And then for all i's greater than k, so you essentially have, let's say, P here, if you use this formula, mu times Pk plus 1 equal to lambda times Pk So pk plus 1 is equal to rho times pk, right? And then pk is equal to this quantity, right? pk is equal to rho times p0, 1 minus rho to the power k by 1 minus rho, something like that. So similarly, you can derive, and so you will get a multiplication of rho for every subsequent, right? So pk plus 2 will be rho times pk plus 1. So you will have like a rho square times pk, where pk is the same quantity, which is here. This is pk, right? So then what will be the general formula? So in general, we'll have pi equal to rho times I minus k plus 1, and yeah, so you have something like this. So rho times I minus k, rho times I minus k times pk, which you can write as rho times I minus k plus 1 times this summation 1 plus rho to the power k minus 1 p naught. So it's, yeah, that is kind of the, this is for all I greater than or equal to k, which is when it just behaves like a normal MM1Q. And so eventually, so then what you will do is you'll plug everything in this massive equation, which is the sum equation. So p naught times, which is that the sum of all probabilities equal to 1, k plus summation I equal to 1 to k, this thing, plus 1 minus rho to the power k. This whole quantity is nothing but 1 minus rho to the power k by 1 minus rho. 1 minus rho times rho squared. So this whole thing can be solved. And after quite some calculation, what you will get is P0 equal to something like 1 minus rho by k. Something like this. Okay. So then, yeah, once you have P0, okay, so once you have P0 and you have all of the other, you can obtain all of the other Pns, you can obtain this summation n times Pn n equal to 0 to infinity, and so on and so forth. One intuitive way of obtaining the same quantity is that recall that the probability of being blocked in an MM1Q is nothing but 1 minus rho. And so now there are k number of blocked states. So which are 0. Oh, I lost you for a bit. Okay, let's wait. Hello. Yeah, I lost you for a bit. So this is just a quick intuition that in an MM1Q, the probability that you are blocked even in a regular MM1Q, that is like the probability that it's usually P0. is 1 minus rho, right? Probability that you are idle. And so now you have k block states because you have all of these states 0, 1 prime till k minus 1 prime. When you won't be doing any service, you're kind of blocked because you will only start service when you reach the state k. So, and then they are all of equal probability. So you will have P0 equal to P1 prime equal to equal to 1 minus rho by k. So then it's quicker, it's kind of an intuitive way to derive the same quantity. But once you have P0, you can calculate all of the Pns, and when Pn prime is already known. And so you can compute the average occupancy of the queue as well. So all of these, then it's just calculation after a point. And so if you solve, the average number of people in the queue comes out to be k minus 1 by 2 plus rho times 1 minus rho. So this, if you recall, is the average occupancy of an MM1 queue. And you have this additional term, which is the extra states that have been generated because you are not allowing service. So yeah, that is there. That is the additional term there. And then the expected time is nothing but n by lambda, right? Because this is by Little's law. So no matter what kind of queue, what kind of arbitrary distribution, Little's law will always hold. So yeah, this is a little bit calculation heavy, but it's simple. It's an intuitive problem that if you change a small thing, how does things differ? Okay. Hope this is clear. Let's then move on to a new problem. So okay, so this is problem number 3.16. And so here, what you have an MM1 like system, but the arrival rate lambda n and service rate mu n depends on the value of n. So it depends on n. So normally what we have in an MM1 queue is you have all of these states. So you have arrival at rate lambda, departure at rate mu, arrival at rate lambda, departure at rate mu, so on and so forth, right? So let's say if I have to draw here, sorry, n minus 1 and n plus 1. So you have arrival at rate lambda, departure at rate mu. Now what happens if we change this to dependent rates? So these are, now if we have different quantities, if we have lambda 0 and mu 0, so this is, yeah, sorry, this will not be mu 0, this will actually be mu 1, lambda 1 and mu 2, so departure from service rate at state 2. And similarly, you have lambda n minus 1, mu n, lambda n, mu n plus 1, so on and so forth, right? So this is the change that we have now in the system. And so what we want to find out is, again, the probability of the state n. So what is Pn? And so what we have to do is we have to show that Pn plus 1 equal to something like rho 0 multiplied to the rho n P naught where rho k is lambda k by mu k plus 1. This is like a generalized MM1Q, if you might call it. So rho k is nothing but if you draw a dividing line here, lambda 1 by mu 2 is, so rho 1 will be lambda 1 by mu 2. Similarly here, rho 0 will be lambda 0 by mu 1, so on and so forth. So you have to show that, you have to prove this. How will you do it? And so obviously, if this holds, then the second thing, showing the second thing is easier, which is P0 equal to 1 plus summation k equal to 0 to infinity rho k whole inverse. Well, actually, it is. Yeah, well, I can just denote it as n instead. So one thing obvious that if you sum over all Pn, n equal to 0 to infinity, this comes out to be 1, right? And so if for a second, if we assume that the first part is correct, if the first part is correct, then what we have is P0 plus P0 times P0 plus P1. And so let's just write it out. P1 will be rho 0 times P0, right? P2 will be rho 1 times P0, so on and so forth. So if we break the summation, then what we'll have is P0 times 1 plus, sorry, P2 will be rho 1 plus P1, which will be rho 1 plus, sorry, P2 will be rho 1 plus rho 0 times rho 1, Pn plus 1, this is n plus 1. So this will be n, rho 1 times P0. So this will be nothing but P0 times 1 P0 plus rho 0 times P0 plus rho 0 times rho 1 times P0 and so on and so forth, right, till infinity. This is equal to 1. So I can write it as P0 times 1 plus n equal to 0 to infinity, rho 0 till rho n equal to 1. Because just all we need to do is take P0 common, you'll have 1 plus rho 0 times rho 1 plus rho 0, rho 1, rho 2, so on and so forth. So this whole summation will be there. And so then P0, obviously, if you just divide both sides, you will get 1 plus summation n equal to 0 to infinity, rho 0 till rho n, whole inverse. So what we have is, if the first part is true, then obviously we have proved that the second part is also true. So now, obviously, the challenging part is to prove the first part. And so how do we go about it? Okay, so let's like quickly write down the local balance equations, and we can do it by splitting the Markov chains here. So we firstly have lambda 0 times P0 is equal to mu1 times P1, right? So lambda 0 P0 equal to mu1 P1, which means P1 equal to lambda 0 upon mu1 times P0. And by definition, we have rho k as lambda k by mu k plus 1. So we'll have rho 0 as lambda 0 by mu1. So this will be rho 0 times P0. So yeah, so we have, let's say if you're using some method of induction, we know it is trivially like this. We want to prove this quantity, right? Rho n plus 1 equal to this times P0. Now, So this is for n equal to 0, we have proved. So this is proved for n equal to 0. For n equal to 1, again, we can kind of draw a line here. So we'll have lambda 1 times p1 equal to mu2 times p2. So lambda 1 times p1 equal to mu2 times p2, which implies p2 equal to lambda 1 by mu2 times p1. So lambda 1 times mu2 is again rho 1 by definition, and p1 has already been proved to be rho 0 times p0. So then we have this holds for n equal to 1, and similarly we can just carry on this line of proof. So what we'll get is, in general, Pn will be, or like instead of writing as rho 1 times rho 0, I could have also written it as rho 0 times rho 1. And so similarly, you'll have rho 0 times Pn plus 1, you'll have rho 0 times rho 1 times rho n times P0. You can kind of just keep on doing it. So this was an easier problem, I think. This is a more generalized version of an MM1Q, where you have state dependent arrival and service rates. Okay. So this kind of variations you can get. And you need to know how to solve. Okay. So let's go to the next problem. So here, I'm going to problem number 3.19. So you have a telephone company. Okay. You have a telephone company, let's say Vodafone or Jio, any of these. So you have two cities. So you have two cities, A and B, and it establishes a direct kind of wired line between these two cities for telephone calls. These are old days. And so the rate of call which it anticipates between these two cities will be something like 30 calls per minute. So there'll be 30 calls per minute between these two cities. That is what they anticipate. So this is, let's say, lambda. So you have a queue of calls here. And so then obviously lambda is equal to 30 per minute. And then the duration of the calls, 30 calls per minute, and exponentially, and so 30 calls per minute, this is Poisson traffic. Poisson traffic, 30 calls per minute. And the duration of the call, so once you make a call, the duration is exponential. Exponential with mean is 3 minutes. Now, by the neat trick, we know that if the duration of calls is exponential, that means the rate at which calls are being completed is actually Poisson. And so the mean rate mu, so this mean is nothing but 1 by mu of the service rate. So the mu will be actually 1 by 3 per minute, right? So then the rate at which calls get completed, which is, so this is a queue of calls, right? The rate at once a call is completed, it will drop out of the queue, right? So the rate at which calls get completed is mu equal to 1/3 per minute. 1/3 calls get completed in a minute. Okay. So and so what you're trying to figure out is number of circuits. So these were olden days. Each call, so it was analog communications. Each call was handled with an actual circuit, calling circuit between two cities, right? Number of circuits such that probability of failure or probability of call drop is less than 0.01. You want to find out the number of circuits that you need such that probability of call drop is less than 0.01. Okay. So how do we solve this problem? So this kind of queue is modeled by this MMMMQ, right? So where M is number of circuits. Why? So you have the arrival and the departure process in the queue. Both of these are Poisson or exponential, as I explained, because yeah, so that is by design. And so you have M circuits. So at any single moment, you can be served by M servers, right? So there are M servers available. However, you also have a constraint that you cannot have more than M servers, or like you essentially have to reject all calls after M. So you cannot have more than M calls waiting. So then you have this kind of a modeling. And so we know that there is the Erlang B formula for this kind of a system. So the probability of the state M, where M is this limit. So here you won't be serving more than M calls. So we can calculate the probability of M is nothing but lambda by mu whole to the power M upon M factorial divided by summation n equal to 0 to M lambda by mu whole to the power n by n factorial. So this is the Erlang B formula. This is the probability that, because once you are in state M, once there are M elements in the queue, any M calls in the queue, any incoming call will be dropped. So you will have a call drop. So this is nothing but this is the probability of call drop actually, because any calls after this will be dropped. And so you need, and so we have lambda equal to 30. We have mu equal to 1/3. So lambda by mu is equal to 90, right? Lambda by mu equal to 90. You can plug this in. And so what we need is essentially 90 to the power m by m factorial divided by summation 90 to the power n by n factorial, n equal to 0 to m. We need this to be less than 0.01. So then this kind of thing can only be solved using like a scientific calculator or on MATLAB. And also you have Erlang B tables. So yeah, so you have to use Erlang B tables online. You can find them out to solve, and then you will essentially get the value of m. M equal to question mark. You can find it out. So as you solve, you will get this value of m. That this will be the number of circuits that you will require. So this principle, this is how telephone lines were designed in olden days. So this is one problem. Okay, so let's pick another problem now. So we'll do this. I had introduced this problem earlier, but now that we know more about queues, we'll solve it more rigorously. So you have some kind of facility in a city where you have 5 tennis courts. 5 tennis courts. And so in a tennis court, what again, you can, in this facility, you can view this as a queue. So you have people arriving, and then you have 5 courts here, right? So it's like so you have like five courts. People arriving, and then you also have players leaving, right? So people are arriving at a rate, again Poisson rate of 1 pair per 10 minutes. You will need pairs to play tennis. It's not an individual game. So you'll have 1 pair plus per 10 minutes. And then once a pair arrives, once 2 players arrive, they will use the court for an exponential time of mean 40 minutes. So the duration, so then mu is equal to, so this is lambda, and then mu is equal to, actually 1 by mu is equal to 40 minutes. So this is the average time. So exponential, and average time spent at the court is 40 minutes. Exponential distributed. So this converts to Poisson departures with a rate mu equal to 1 by 40 per minute, right? So the first part is, let's say, so 1 pair arrives. 1 pair arrives. So what this pair finds is courts are busy and K pairs are waiting. So there is all the courts are currently busy and they have K pairs waiting in front of them. So what you want to figure out is average waiting time for this situation, right? So how do you solve this kind of a problem? Okay. So now when all courts are busy, so you have you essentially, and you want to find out the probability that one of the courts, you want to find out like the expected time between 2 departures from all courts combined. So by the property of exponential variables, you can actually prove that now for 1 court, the expected time between 2 departures is 40 minutes. But now you have 5 courts, so 5 identically distributed exponential variables. So that's what you want to figure out, right? 5 identically distributed exponential variables, and you want to find out the minimum of 5. So even intuitively, if you have 40 minutes as the average waiting time in 1 court, if you have 5 courts, your waiting time will be 40 by 5, which is equal to 8 minutes, right? Because when, like, even intuitively, when 1 pair is playing, you might have a chance that the other court gets empty, and like it's all of the courts are kind of equivalent. So even intuitively, you can think of it that okay, the average waiting time for at least one of these courts to be empty will be 40 divided by 5, which is 8 minutes, right? So then at any time, if all the courts are busy, so then there is one wait of 8 minutes. And then for each of these pairs, you have an average wait of 8 minutes more. So this is 8 times k minutes. So in total, you will have to wait for 8 times k plus 1 minutes. That's the answer, really. So you'll have to wait for 8 times k plus 1 minutes. And then the second part is, so this is more like an intuitive solution. So now second part is, you want to find out the average queuing waiting time in general. So this is like more like EWK. So you have k players waiting in front of you. So you want to find the average waiting time in the queue in general. So kind of like averaging over all values of k. But we have a different way of solving it. We know queuing theory. So the average, yeah. So here we have arrival rate as 1 by 10, right? 1 pair per 10 minutes. And service rate is 1 by 40. And so you have the value rho, which is lambda. And remember, this is an MM5Q, because you have 5 servers, you have 5 quotes that kind of empty the queue of waiting players. So the queue builds up somewhere over here. And then you have 5 quotes that can empty the server, like 5 servers. So the value of rho, what we usually take is lambda by C mu. So in this case, it will be lambda by this quantity C. So lambda by 5 mu. So 1 by 10 by 5 times 1 by 40, that's 0.8. And so by and then the average waiting time by the results of MMM comes out to be something like rho times something. So this is where PQ is that the probability of queuing actually. Of queuing. So this is average waiting time. So probability that if you are in a queue, then this will be your average waiting time. And so if you kind of, so now in the question you are provided that all the, like, it's actually, I wrote it wrong. You are provided that all the ports are busy. You're provided that all the ports are busy. So what you need is really a conditional probability. So then that expected waiting time, let's say X, will be nothing but you want to find the expected value of W given that there is a queue, given that there is queuing, given that you don't find any quote empty on arrival. So then you will just divide it by the probability, right? So you will just divide W by the probability that there is a queue. So you are assuming that there is a queue, and then this will be your average waiting time, where rho is 0.8. This is rho. This comes out to be 40 minutes. So if you find all of the quotes busy, you can calculate that you will have to wait for 40 minutes to get a quote where you can play. And this was one problem. Okay. Let's solve problem 3.26, and then let's see if we have time remaining. We'll solve some other problems. Okay. So this is just kind of more like a problem where you have to comprehend. So you have, let's say, a facility, let's say a laundromat with M, I'm just taking an example, M washing machines, let's say. M washing machines are there. And there is just one repair person, right? One person who is able to repair, and the repair time is exponential with mean as 1 by lambda, right? Exponentially mean 1 by lambda. And then, so for a machine, and time to fail for a machine, time for one machine to be dysfunctional after. So let's say you have just repaired it and the machine is functioning, and then it will again fail after a time which is also exponential with a mean as 1 by mu. And so you want to find out the time, you want to find out what percentage of time, or like what is the probability that there is no operational machine. You want to find out the proportion of time when there's no operational machine. So here, if you can see, you want to find out the now. So if you define the state as n, which is number of operational machines, right? So once you have a machine repaired, so n goes to n plus 1 at a, again, exponential, the reverse is Poisson. So this is Poisson lambda, right? Because once you have a machine repaired, you have one more operation machine. So you go from n to n plus 1. And then you go from n to n minus 1 when one of the operational machines again malfunctions. So this is again the reverse of exponential. So this is Poisson at rate mu. So this is simply an MM1Q, but we also have a constraint that we have at most M washing machines, right? So N cannot go beyond M. So N can only hold values 0, 1 till M. So then this is clearly, so then we will not be able to accommodate strings M plus 1, etc. Right? So this doesn't exist because we don't have more than n machines. So then this is an M1 because we have only one repair person, so one server, and at any time, only one machine can fail, right? Because it's a completely random thing. We cannot really constrain. We cannot really say that two machines will fail at the same time. So you have an MM1MQ here. So this is just once you identify that this is an MM1MQ, then the probability that you need is simply P0 for MM1MQ. And then once you have all of the values, you have lambda, you have mu, you can calculate. So this is the probability that you will need. Okay. Right. So I will have, maybe since there is some time, we should be able to fit in one more problem. Okay, one or two more maybe. Let's solve problem number 3.25. So this problem is a little, so 1 second. A little complicated. Let's see. So you have a network operator, and so a network operator has M radio channels, right? M radio telephone channels are there. So this is the resource that a network operator has. And the network operator supports two kinds of calls. One is, so from a radio enabled handset to another radio enabled handsets, and also from radio enabled handsets to non-radio enabled handsets. Two types of calls are supported, right? And so for the first one, there are lambda 1, again Poisson, lambda 1 Poisson calls per second, and then these require 2 channels per call. So for each call, you have to block 2 channels out of these M channels for a radio to radio call. And for a radio to non-radio call, firstly the rate of these calls, so these calls happen at the rate lambda 2. But for the radio to non-radio call, you actually just need to reserve 1 channel per call. And then for both of these calls, duration is the same. It's exponentially distributed with mean 1 by mu. So, and then beyond, so then you have the constraint here that you have only M radio telephone channels. So if all M channels are utilized, obviously calls are blocked because you don't have any more resources available to provide to the users. So what you want to figure out is probability of blockage for radio calls, and also probability of blockage Actually, I should write it better. P block for radio calls, for radio to radio calls, and then probability of blockage or call drops for radio to non-radio calls. I want to figure out both of these. And what is the probability that these kind of calls, both kind of calls will be blocked? So this is actually slightly tricky because this requires you to go into like two-dimensional Markov chain actually. So here there are two variables. N1 denotes number of radio to radio calls, and then N2 denotes number of radio to non-radio calls, right? So N1 and N2 are again two different quantities. And clearly we have the constraint that 2 times N1 plus N2 has to be less or equal to M. Why? Because for the first type of radio to radio calls, we need to reserve 2 channels. For the second type of call, which is radio to non-radio, we need to reserve 1 channel. And so then the total number of channels is M. So that's the maximum number of channels that we have. So the number of channels in use is 2 times N1 plus N2, and that has to be less or equal to M. So this is a constraint that we have. So if you have to draw it out in kind of an XY axis, N2, N1. So let's take N2 to be 0. Let's say there are no radio to non-radio calls. Clearly N1 can take values starting from 0 to floor of M by 2, right? Because we do, if M is even, then till M by 2, otherwise it's floor of M by 2, comma 0. So this is the origin 0, comma 0. So this is a maximum possible value of M1. And so from 0, 0 to 1, 0, etc. So all of these transitions are actually, so the rate of arrival of a type 1 call, if I may call it, radio to radio, is lambda 1. And then service rate is mu, because again, service rate of a call is like the duration is exponential. So the rate of departure of a call from the call queue is Poisson with mean mu. So similarly, it will be lambda 1 times mu, and so on and so forth. It will keep on being lambda 1 times mu. So this is on this axis. Now, if you have a call of the second type arriving, so you will go from 0, 0 to 0, 1. So you'll 1. And again, if you put N1 equal to 0 as an extreme case, N2 can take values from 0 till M, right? That's the maximum possible value N2 can take. So this will be 0, M, right? Mu, and again, so this is mu. This is lambda 2. And so you have kind of like this line that 2N1 plus N2 less or equal to M, and you have to stay within the line. Sorry, this line will actually pass through these 2 points here. This, my bad. So you have this point and this point. So this line is essentially 2 times N1 plus N2 equal to M. And all of your values of N1 and N2 have to lie within this shaded area to the left of the line, right? So you can kind of write 2 transition values here, rho 1 equal to lambda 1 by mu, and rho 2 equal to lambda 2 by 1. We're just normalizing by the service rate. Okay. So if you actually solve all the global balance equations at all of these states, you can kind of argue that P of n1 comma n2, this 2D probability, that is nothing but rho 1 to the power n1, because you are going from 0 to n1, so then you'll have a rho 1 multiplier times the blocking probability. So it's kind of like two MM1 Qs multiplied with each other, right? So rho 1 to the power n1 times 1 minus rho 1 times rho 2 to the power n2, rho 2 to the power n2 times 1 minus rho 2. And then all of this is actually normalized by factor G. So you can kind of, I'm just multiplying it here, or I can just write it as 1 by G times, because you are essentially you're summing this over for all n1, n2 such that 2n1 plus n2 less or equal to m. So you're solving it for all n1 plus n2. So you will get, so you need this normalizing factor because G, because eventually you need to obtain this condition, right? That P of n1 comma n2 summing over all n1, n2 such that 2n1 plus n2 less or equal to m. You need the sum of all probabilities to be 1. So if you plug this formula into this equation, you'll get the value of G. So then this will give you G. And so if you solve, you will get the value of G. So then you can do it yourselves, but I'll just write down the final answer here kind of. So there are two cases here. Here m is even, and then you have another formula for when n is odd. So that is 1 minus rho 1 times n plus 1 by 2 minus 1 minus rho 1 to squared. So this is when n is odd, right? Okay. So now you can do the algebra later, but essentially you have the formula for G. So you have the expression for G. So you have the expression for P of n1 comma n2. You have the expression for P of n1 comma n2. Now you want to compute P1, which is probability of blockage of all radio to radio calls, right? And you also want to find out P2, which is probability of blockage of all radio to non-radio calls. So to find both. So now let's calculate P2 first, right? So probability of blockage of all radio to non-radio calls. So then this is essentially summing over all. Now just think about it. For radio to non-radio calls, for each radio to non-radio call, as discussed earlier, you will need just one channel, right? I'll just note it here that this requires one channel. And you have total of m channels. And total number of channels in use is nothing but 2n1 plus n2. So your call will be blocked if and only if you already hit the total of m channels and you have no more channels available, right? Because you just needed one channel and you don't even have one channel available. So then your calls will be blocked if if all of the channels are used or in use. So 2n1 plus n2 equal to m. So your calls will be blocked if you have n1, n2 such that 2n1 plus n2 is equal to m. Now, how do you do this summation? See, n1 can take any range of values from, as you said, like if as an extreme condition, you can have n2 equal to m. So then n1 is 0, or you can put n2 to be 0, then n1 can be at most floor of n by 2, right? So you can just do a summation over over n1. N1 is 0 to floor of n by 2, and then n2 can take values from 0 to m minus 2n1, right? P of n1 comma n2, and you know the formula for P of n1 comma n2, so you will get P2, right? So you can just kind of do the computation, and so the final expression comes out to be something like 1 minus rho 1 times rho 2 squared whole to the power floor of m by 2 plus 1 by 1 minus rho 1 by rho 2 square. This multiplied with 1 minus rho 1, 1 minus rho 2 to the power n by g. It's a messy expression, but essentially this is the way you will proceed with this kind of problem. And then for P1, which is probability of blockage of radio to radio calls. So for radio to radio calls, we actually need 2 channels, right? We need 2 channels. So we can have 2 situations where we have a blockage. We can have 2n1 plus n2 equal to m, that is all channels are in use, or we can also have 2n1 plus n2 equal to m minus 1, in which case we'll just have 1 channel available. But for this first type of call, we need 2 channels. So then again, we'll have a call drop. So then P1 will be essentially summation overall P of n1 comma n2, where n1 comma n2 such that m minus 1 less or equal to 2n1 plus n2 less or equal to m. So you can either have m minus 1 or m. So then this already includes, or like if I write it better in a better way, 2n1 plus n2 equal to m minus 1, or 2n1 plus n2 equal to m. So this case, this summation 2n1 plus n2 equal to m is already included in P2, right? So then P1 is nothing but P2 plus summation Pn1 comma n2 such that 2n1 plus n2 equal to m minus 1. So this is really the additional term that is coming in, because the first kind of call requires 2 channels. And so even m minus 1 available channels will not be sufficient. And so if you solve this, you will get something like this, whatever P2 was, which is this, plus 1 minus rho 1, 1 minus rho 2 to the power m minus 1 over g times 1 minus rho 1 by rho 2 square floor of plus 1 by 2 by 1 minus rho 1 by rho 2 square. Something like that. So anyway, this is kind of the solution. I just wanted to show one problem where you have a 2D Markov chain, or like it's more like two 1D Markov chains, but the Markov chains are not independent of each other. They interact in an interesting way because you have this overall resource constraint here. So yeah, this is the last problem I think that I wanted to discuss. And this was the last one was particularly, I think, quite difficult mathematically and thought-wise. So I am online for 4 more minutes, so I can address any doubts. But I don't want to go beyond MMQs because this itself has a lot of various kinds of problems that you can frame. The possibilities are endless. So yeah. I can entertain any doubts that you have. Otherwise, yeah. Thanks. So yeah, if you are clear, you can leave.